Welcome to Young Tuition, perhaps the only channel focused on physics and art. Let's do some craft work first. Qu'est-ce que c'est? Can you guess? Well, I will show you while I finish this simple craft work. So first, I just cut that. Let's see. It's triangle, right angle triangle. Then I will cut. Perhaps you can see what I'm doing. So that's it. Look at triangle. But this would be part of my 3D model to describe the electrical potential distribution in the circuit. And this is another one. You see that? Cut. And I could do craft work, doing craft. Yes, I remember when I was kids, I just enjoy making things, crafts included. All right. So I just quickly cut the two shape. Okay. Okay. Perhaps this way, this way, this way. You see? The origin color, different shape. What does that mean? Well, that represents the potential distribution in the DC circuit. Here is a toilet paper roll. Oh, can tell you it's quite rare because we couldn't buy toilet paper for nearly 1 month. So this is very valuable. So I've put some stick already, so that we can do this craft very quickly. So what I'm going to do is just to roll this orange color paper around the toilet roll. Yeah, nearly finished. So this is one of them. So this is one of them. From here, you can see this is a circle, right? And the height of this cylinder will represent the electrical potential. For example, this is a loop. If you consider there's a battery, DC battery here, and you will obtain this kind of the potential difference. I will go to detail after I finish another one. So this is another toilet paper roll. And again, I just remove this sticker, double-sided sticker, very useful. Oh, it's me. Huh. Yes, please subscribe and please make any comment, no matter how short the comment is, which is very important to promote this channel. You can see I can put more video on both physics and art. Oh, by the way, recently we also initiated another video series called Life and Electricity. Anyway, let's return to our, so this is another 3D model for the potential distribution in the cylinder loop, or some people call it Professor Lewin-Loop. That's fine. And so from this cross section, you will see the circle. It's a loop, and the height illustrated by this orange color will represent that the potential electrical potential distribution. All right. So that's it. We are going to use these two 3D models soon, and without using computer. Okay, what's the point to use computer if it doesn't provide new ideas? Let's go to the screen. Last week, I proposed a simple hypothesis to explain the electron density distribution in a DC circuit. Now, this is a relevant diagram in which I point out the fundamental difference between the electron density distribution in a capacitor and a resistor. So from here, you can see that the density current, the density of electron has different distribution in the capacitor from the resistor. The important implication of this hypothesis is that we can explain the electrical potential distribution across a capacitor and a resistor in terms of the both electron density and the electron drift speed. So that is how we have achieved in the last video. Today, I'm going to extend this idea to the circular loop or Lewin-Loop, so that we can apply this hypothesis to explain, the electrical potential difference and the experimental observation. Let's go. This is actually historical issues. Some reference can be traced back to as early as 60s. So here we are. We have the two circular loops, and with each of them has two resistors. So it's a standard setup to study the Lewin-Loop. However, the loop on the right-hand side is driven by a battery. The one on the left-hand side is driven by the changing magnetic field, or magnetic field flux to be exact. And so that we can compare the two scenarios based on the hypothesis I just made. Now, in this diagram, in the first diagram, we can follow that the description we made a few weeks ago, that the induced EMF is evenly distributed along the loop, so that if you follow that direction, here we just put at this point, I assume at this point, the electrical potential is 0 or is Earth. So based on this choice of potential reference, then we can easily draw these two diagrams. So that is exactly what I have done here. So that is the one. Let's go to the simple one. So this is for the DC battery. So this is a circle. So if you follow this one, you can see the potential distribution along the circle, which include the two resistors. So one of the two point of interest is called A and B. Here you can see that in this particular setup, the potential at A is higher than potential at B. However, in the case of the circular loop, in the absence of battery, bear in mind, then you can see that the potential at A is lower than potential at B. Okay, that is some details. Some is fundamental difference between the two circles. Furthermore, we can discuss different scenarios. For example, if on the two resistors in the loop are identical, then we would obtain these two diagrams. Again, in the case of the battery-driven circuit, you can see that the voltage at A is still larger than voltage. Sorry, the potential at A is still higher than the potential at B. However, in the case of the circular loop, in this particular case, the electrical potential at point A and B are identical. Of course, you can consider the different scenario in case, for example, if we just consider R1 is larger than R2, we can get a different profile. And the one we built today is just for the first scenario. In summary, you can see if the current is driven by the battery, the single battery, then the potential difference between A and B is always positive and constant. Not necessarily constant. The potential at VA is always larger, higher than potential B. However, for the circular loop, the current is induced by the changing magnetic field flux. You can see that the potential difference between A and B can be different, either smaller, equal, or even larger. So that is this is my result based on the hypothesis of the density, electron density distribution, so that we can work out the voltage, the potential distribution. Here is another detailed discussing. So based on this fact, so the upper two diagram will represent that the one is a circular loop, in which the current is induced by the magnetic field flux change. Another is driven by the ordinary battery. In both cases, the electrical current you could measure at any point of this loop is constant. However, both electron density and the drift speed of the electrons are different. In the case of the DC-driven loop, we see this horizontal line to represent the drift speed and the electron density. However, in the case of the circular loop, in which the current is induced by changing magnetic field flux, you can see that electron density increase linearly, while the drift speed decrease linearly, so that we can still explain the current. You still can explain the observation that the current is constant. The reason that we introduced this idea of the electron density distribution along the loop or in the DC circle is that we notice that there are some people who, without this in-depth thinking, merely fabricate some electron density distribution, such as this one. Let's have a look. So this is one of example in which the electron, or they call the charge density along the circular path or circular loop is generated by a computer program. It looks real because this is done by using a computer. However, no explanation, no physical explanation can be found, as admitted by this author, that he actually have no idea how to the silicon soup. I saw your other videos with lots of math. They were really impressive. However, I didn't try to derive relation for the charge distribution, as I think it is probably very complicated, indicating this guy didn't use any physical theory to justify this diagram. Pretty new, yeah, good looking. So that is my discussing today. I hope you enjoy watching this type of discussing, and hopefully you can build this 3D model by yourself based on the electron density distribution in the circle without using any computer simulation. Please like, please subscribe, and please make any comment to promote this channel so that I can make more relevant videos. Thank you for watching. Goodbye.